Hi class, now we're going to go over the next and last chapter, which is chapter 11. 11.1 is quadratic forms. So this is how we are going to relate linear algebra to conic sections, basically, right? So hyperbolas, ellipses, parabolas, things like that, okay? So let's go over definition first. So a quadratic form is a function, which we'll call Q, from n space to R, right? So you're going to have a vector and you're going to end up with a single value, a scalar, that has the form Q of x equals x transpose times A times x, okay? Here A is going to be an n by n symmetric matrix. They will always be symmetric, called the matrix of the quadratic form. So we've been talking a lot about symmetric matrices previously with our QR factorization and our singular value decomposition. So we can do all of those kinds of things here as well, although this is a completely different section, right? So let's do an example, very, very basic example, just to kind of explain and show a concrete example of this definition. Let's say I have a vector, x1, x2, so it's unknown what the values are, and I have some basic matrix here, which is this is obviously symmetric, right? It's a small 2 by 2, it makes it easier to kind of understand, and it's diagonal, which is also pretty nice, okay? So if I just show what the quadratic form is, this x transpose AX, I will have x1, x2 in the horizontal form times this matrix times the vertical form, okay? So what I'll get out is I'll just multiply one at a time. So I'll multiply these two and then that result times this, or I guess I can go these two and then that result times that. It doesn't really matter. But I'll get 3x1 squared plus 2x2 squared, okay? And that is my quadratic form. That's the formula I have for basically the polynomial form by this matrix, right? So for a theorem, let's say that A is a symmetric matrix. So of course it has to be n by n. Then there exists an orthogonal matrix P, such that if I want to create a vector y, I can create that vector y that will be the transpose of this P times x vector, okay? And that's going to change my quadratic form that I have here into a new quadratic form of the form y transpose dy. Now you might be saying, what does this even mean? Well, here I had a diagonal matrix. Diagonal matrices have nice results for us. If my matrix is not diagonal, basically what I'm saying is that I can diagonalize it to have a equivalent, similar form, okay, which is diagonal in form, okay. So there will be no cross product terms, okay. So we haven't talked about a cross product terms. There were no cross product terms here. A cross product term is what happens when my matrix is not diagonal. It basically means I have a mixed term here, right? So there's no x1, x2 term. It's only x1s, only x2s. There's no plus 5 x1, x2, right? So an x1, x2 term would be considered a cross product term, okay? So the thing with diagonal matrices is that there are no cross product terms, which gives me a nice, clean sort of quadratic form out, okay? So let's do an example. So let's take an example that is not quadratic, and we will basically, it is quadratic, but not diagonal in form, and we will basically diagonalize it, okay? So let's find a change of variable to express this quadratic form, A2112, which, again, I've used this maybe in 3 different videos already, right? So this is a common example because we have results for it already. So that's why I'm choosing it again. So I want to diagonalize this basically. I'm going to do a change of variable. So from x's into y's, where my terms and y's have no cross variables, okay? No cross product terms. So note that if Q is this quadratic form, then it will have, if I slowly multiply this out, okay, so x1, x2 times 2 and 1 will give me this. x1 plus 2x2 gives me this term, times this. As you can see, I have cross product terms here, okay. In fact, these are the same, so I can add them together. This is what the simplified form of my Q for A looks like, okay. So what I want to do is I'm going to do a change of variable so that I don't have x's, I have y's, and there is no cross product term. That's the goal here, okay. So we need a matrix P that orthogonally diagonalizes this A, okay. So P will be an orthogonal matrix. So remember, that means the column vectors will be orthogonal to each other, and they will also be normalized, right? So let's do the characteristic polynomial because I need the eigenvalues here and the eigenvectors. So if I start to find the characteristic polynomial, I have lambda minus 2 squared minus a positive 1, because negative 1 times negative 1 is positive 1. This expands into a nice form, which can be factored again. And these are the eigenvalues that we have. Again, we've done this this is like the 4th or 5th time we've done that to this matrix now. So you should have these results. So that's why I'm going through it semi-quickly. Okay. And we know what the eigenvalues, the eigenvectors for this are as well. I'm not going to go through the whole thing. You should have this a couple of times already in your notes, or you can do it all from scratch again. That's fine. But you should definitely know how to find the eigenvectors. So my eigenvectors are -1, 1 and 1, 1. Okay. So these are the eigenvectors that I get from their associated eigenvalues, right? Now, again, my P is made up of the eigenvectors for these eigenvalues, and they need to be orthonormal, right? So obviously you can tell just from looking at it, the dot product between lambda 1 and lambda 2 is 0, right? -1 plus 1 is 0. So they're already orthogonal, but they need to be normalized as well. So P1 is x1 divided by the length of itself, which gives me -1 over root 2, 1 over root 2. I'll get the same thing here, but all positive, 1 over root 2, 1 over root 2. Okay. So now that I have these, my diagonal matrix is just going to be the eigenvalues of lambda 1, lambda 2. Okay. And my P matrix is going to be made up of these column vectors in the same order as the eigenvectors. So P1 and P2, because they go with the eigenvalues, right? So that's my D and my P. So now I can use these formulas that I had, right? This Y vector, remember, is going to be P transpose times X, but we've seen before this P transpose is just P because we're just going to switch these diagonals. It's not always the case that they're the same as P, but in this case it is, mainly because it's a 2 by 2 and it's symmetric, right? So so when I do the transpose, in this case it's the same as P. And so for Y, I'm going to just kind of throw this stuff together, and then if I take that Y and I throw it into here, it should be the same. So it's just a change of variable. Okay. So Q of Y is going to be y1 squared plus 3y squared, right? And that should be clear because of the diagonal form here. Okay. So if I were to plug in Y into this equation, right? Y transpose dy, that's what I'll get. Okay, but now if I want to look at what Y actually looks like, okay, we need to kind of choose a particular value to kind of plug in. So let this value we're going to look at be the vector 1, 2. So if I plug that into my original Q in terms of x's, right, so the x transpose AX, I'll have this out. Okay, so again, since I'm plugging in a vector that I'm calling x, I got to plug it into here because this is x transpose AX. That's when I'm in terms of an x matrix or x vector, right? So I'm plugging that into here. 2x1 squared plus 2x1 x2 plus 2x2. So remember, x1 is 1, x2 is 2. So then when we come back here, this is what we have, right? 2x1 squared plus 2 times x1, x2 plus 2 x2 squared, right? And I will get out 14. 2 plus 4 plus 8, okay? So that's 12 plus 2, which is 14. So now, just to make sure that these are equivalent, right, I need to find this y. This y is based off of this choice of x naught, okay? So I'm going to take the transpose of p and multiply it times my x vector here, okay? I'm going to get 1 over root 2, 3 over root 2, okay? So now that I have a y, this is what y looks like, okay? I can now plug it in to my y transpose dy, okay? So that's my d. This is the formula I would get out from that. So now I can just substitute my terms because I've already found the quadratic form for it, right? So plugging this into q of y, right? It's going to be your y1 squared plus 3 times your y2 squared. So this is going to give me 1/2 plus 3 times 9 halves, okay? Which is 1/2 plus 27 over 2, which is 28 over 2, which is 14. I get the exact same thing out, okay? So they are equivalent in form. They're going to give me out the same values, right? As long as I transform this x into y before I plug it in to the y form, okay? So again, we have equivalent forms. One has no cross terms and a change of variable. The other one is the standard form that you would look at, okay? So let's look at the geometry of these things, okay? So again, remember, these are quadratic forms, parabolas, hyperbolas, ellipses, things like that, right? Conic sections. The column vectors of P, which are really just the normalized eigenvectors of A, that A matrix that we have, okay? These are called the principal axes of my quadratic form, okay? Which is the x transpose AX, right? So the eigenvectors are the axes that we graph our quadratic forms onto, okay? So we'll make that clear in a second. For C, a scalar, okay, A being an invertible symmetric 2 by 2 matrix, the graph of x transpose AX is going to be in R2 in this case, right? So on an XY plane, and it's going to be an ellipse, a circle, hyperbola, 2 intersecting lines, a single point, or an empty set. Okay, so if we're talking about a 3 by 3 matrix, we're going to be graphing 3-dimensional figures, right? A saddle, a cone, right? A hyperbolic plane. It'll be something in 3 dimensions. So 2 by 2s are easy because we're graphing them in the standard Cartesian R2 coordinates, right? So let's consider a matrix A that is diagonal, okay? If A, B, and C are all positive, then the quadratic form we get from this is A x1 squared plus B x2 squared equals C. And this is going to be an ellipse if we have an addition in the middle and everything is positive, okay? And our ellipse can be graphed easily in this form, okay? Square root of C over this B term is going to be the minor axis values, right? That'll give us the length of the minor axis. It'll be root C over B. And root C over A will be the major axis, okay? The long axis. Now, this is when it's in diagonal form, okay? If we're graphing our original function, the eigenvectors make up the major and minor axes. So we will have some sort of a reflection or rotation going on here based upon what my eigenvectors look like. Okay, so this is in a diagonal form, right? So basically when we do this, we look at the diagonal form and then we translate that with a transformation based on P into what the actual graph is going to look like, right? So we use this because this is easy to graph. You're going along an axis, it's fine. So then what we do after that is we look at the eigenvectors, and then we just transform this based upon the eigenvectors. Okay. So when there is no cross product terms, our equation is said to be in standard form. And the eigenvectors of A, they form the coordinate axes for my translated function. So you might again be like, what are you talking about, Professor Williams? Obviously, we're going to do an example. Okay. So let's take our previous example. Okay. And let's set it equal to 40. So 2x1 squared plus 2 of these, right? I should have just added these together. I don't know why I kept it separate. Plus 2x squared 2. Okay. So we're looking at what we had from A, that quadratic form, and we're just going to set it to an arbitrary number. In this case, let it be 40. We're going to graph what the solutions to this look like. So we already diagonalized this, right? We found the diagonal matrix, and we found that P matrix, the vectors, right? So if we want to graph this, then again, graphing the diagonalized Q of Y form makes it way easier. Okay, so we're going to do that first because it's easy to find that. We have, again, formulas for finding the endpoints of the axes, and then we can just draw an ellipse to connect them, right? And then we can translate that according to this P matrix for the actual answer. Okay, so I know maybe you can't see it too well. I graphed this on Desmos, but we're gonna have so again, remember it's square root of C over B for the minor axis. So in that case, remember this was A and this is B. So square root of C, which is 40, over 3 will give you 2/3 square root 30. Okay, so again, square root of 40 over 3. You get to pull out a when you rationalize your denominator, I should say, right? You can pull out a 4 from the 40, which turns into the 2 on the outside, right? And then you multiply square root of 3 top and bottom. So on the bottom, your square root of 3 turns into a 3. That's why you have the 2 root 3. Then in your numerator, you're going to have the square root of 10 left over from that 40 times that square root of 3 that you had. So that's why you have square root 30. Okay, so you should definitely kind of verify that, right? So square root of C over B is square root of 40 over 3, right? So if you rationalize that, you should get 2 over 3 times the square root of 30. So that is my principal axis, top and bottom. Okay. Give me 1 second. I'm going to make this a little bit bigger for you guys to see. Actually, I'll pull up an animation for it. I think will be easier. Okay, so I'll do that in just a second to help you guys see this a little bit better. So the ends are going to be my A, right? So that's square root of 40 over 1. So square root of 40 simplifies to square root 10. So that's how far I am on both of these axes. And that's in terms of the diagonal, right? Q of Y. So when I put that into terms of the actual translation, what I'm going to do, this is a transformation now, okay? I transform and I translate this based on this. So let's think about this two ways, okay? One, this vector creates one axis, the x-axis. This vector creates the new y-axis. So now you're like 1 over root 2, 1 over, like, I don't know what that's going to be. That's fine. What was it before? -1 and 1. So if I go -1, right? It goes x and y, x and y. So -1 up 1, that's that vector. Okay, so that's actually a vector along the line of y equals -x. Okay, so that means that this long axis is now going to translate along this axis. And this is 1, 1, so 1 and 1. So then this minor axis is going to translate in that way as well. So this whole thing is going to rotate. So before I even show that, let's think about this again. This is a rotation matrix, right? Do you remember what our rotation matrix looks like? It looks like cosine, negative sine, sine, cosine, or something to that effect. for sine and cosine to have a value of 1 over root 2, that means that you are translating or rotating by 45 degrees. Okay, and so if I'm going from a vector that is along the axis to one that is at 1, 1, that is a 45-degree rotation, right? If this is 90, a vector at 1, 1 is straight down the middle. Okay, my translation now looks like this. It has been rotated according to these vectors, negative 1, 1, right? Negative 1, 1, and 1, 1, 1, 1. And that's a 45-degree rotation. It's very easy to see that this is a 45-degree rotation of this matrix. So my original form, this form that I actually want, Q of x, I find by first graphing the diagonalized form and then applying this rotation transformation matrix, which is made up of my eigenvectors, to get my actual value. So what was 2/3 square root 30, it's still the minor axis, and it has a length of 2/3 square root 30. So let's actually go to the animation of this. It's not necessarily an animation because I don't know how to. If I spend more time, I can actually transform it and rotate it in Desmos, but I'll just show you guys a nice bigger graph where you can see this play out. So abracadabra, let's see it. Okay, so now we are in the world of Desmos. This is my graph. This is what it looks like when we graph the diagonal form. Obviously, things in Desmos are they're decimal approximations, right? So, and I can't write an actual formula here on Desmos, not for square roots at least. But if you want to look at what these values actually are, right? We can let's take these labels off for a second. If you ever wanted to kind of like double check what that value is, 2 square root 10 should give you negative 6,325. Okay, so that's the length here for both of these axes. Okay, so from 0 to here, that's length along the major axes. Okay, so let's take this one off. Let's label that. Okay, this is the positive form of that. That's the length. Okay, so we can check this when we look at the next matrix. Now for this one, okay, up top, its length is 2.582. So if you were to plug 2/3 times square root 30, you should get 2.582. Okay, that's our check, right? So that's the actual decimal approximation length here, which again in this class you never give me actual decimal approximations. Everything needs to be exact. Okay, I'm just trying to show you guys that something works here. So let's go ahead and I guess I could have left those on for each one of these. Okay, so let's look at our other ellipse. Okay, so again, I don't have an animation for it, but we can just take a look at it and look at what it looks like. Okay, so if I kind of take some things off one at a time to look at, okay, this is the translated form. Okay, this is what we had before, and then it's very easy to see how it has been rotated. Okay, now the eigenvalues that we had were again negative 1, 1, right? Negative 1, 1 was that eigenvector, and so if you look at the first principal axis, okay, running along this way, it goes through that point negative 1, 1, right? Everything is identical here. Okay, and so as you can see, I have 4.472. Okay, that is where this endpoint is. So to check that these are the same, what you would need to do is notice that this is a triangle. Okay, this forms a triangle with a length of 4.472 and a height of 4.472. So if you find through the Pythagorean theorem, the length of this side here, right, from the center to the endpoint of its principal axis, okay, you should notice that that length is square root of 10, okay, which is exactly what we had for our other matrix, okay, 2 square root of 10, right? So, so that's what you should get if you double check. Even with your approximation, you'll get pretty much the same thing out, okay? Now, if we look at the minor axis, it's the same deal, okay? If you go over 1 and up 1, okay, that was the basis vector, okay? We normalized it to 1 over root 2, 1 over root 2, but, you know, if we unnormalize it, it was 1, 1. That was the vector, right? So now that is going to be the axis that I'm on, right? And the length that I have for that, okay, is 2/3 square root 30, right? So it's the exact same, thing that we had before, okay, but translated, okay? So it transitions 45 degrees, okay? There's been a 45-degree translation, and we can tell it's been a 45-degree translation, or rotation, I should say, because of that rotation matrix that we can look at from my P matrix, okay? So think about that P matrix as the transformation matrix for the rotation or reflection that we're going to have for the actual graph that we want to look at, okay? So when you look at these, that's how you should think of this. Again, this was the diagonal matrix Q of Y that we graphed, and then we translate that or rotate it according to the either you can think about this as a rotation matrix and you can figure out what the angle is supposed to be. In this case, it's a nice angle, or you can think about these as the new vectors, like a change of basis. That's basically what we're doing. We're doing a change of basis sort of transformation here, okay? So let's talk about if it's not an ellipse, okay? If we have a plus in the middle, I'm sorry, a subtraction sign in the middle, but all of our coefficients are still positive, but if there's a minus in the middle, then we're going to have a hyperbola instead that has slant asymptotes of x2, which I guess you can think of as like your y, of square root of a over b, right? Plus or minus. So that's going to give us one positive sloped slant asymptote and one negative sloped slant asymptote. And we would graph it the exact same way that we graph an ellipse, which is we diagonalize, we graph that diagonalized form, okay? And then we translate that according to our matrix P, okay? So rotate or reflect according to our transformation of our P matrix, right? So again, in the D form, this is the formulas that we have for everything, okay? So apologies, this should have said times x1, but x1 is a variable anyway, so it doesn't really matter. Because otherwise you would think that this is a constant, so it's times that variable, which is why it's a line, okay? And that's the way that it works. So let's go over definition, which is going to help us a lot going into the next section, 11.2. And it has to do with what's called positive definiteness. Now, I'm going to say this, that when I was taking my graduate level classes in applied mathematics, I heard the term positive definite and semi-positive definite all of the time. It's a very, very, very common term. So these are very, very important forms when talking about applications of things. And that should make sense because we are talking about conic sections, okay? So positive definiteness has a lot to do with optimization, maximums and minimums, a lot of that kind of stuff, because if I am positive definite, which we'll get into in a second, it means I have a minimum value, right? Which is what we want to get into when we're talking about optimizing things. I want to have, I want to minimize or maximize something, okay? So our definition for a positive definite is that our quadratic form here is positive definite if it is larger than 0. It has to be positive for all x in my domain, okay? As long as x is not 0, right? Not the 0 vector, okay? That means, it basically just means that my quadratic form is always positive, and it'll never be 0, right? Unless I was to plug in the 0 vector, okay? And it is called positive semi-definite if I'm 0 or larger for every vector. That means I can be 0, even if I'm not the 0 vector, I can still be 0, but I can never be negative, okay? And that's for every x inside of my domain, in my space that I'm working with. Negative definite is the exact same thing as positive definite, except that I'm always negative, okay? And I'm never 0 unless I'm at the 0 vector, okay? And I'm negative semi-definite if I am negative everywhere and sometimes 0, okay? I know there's a lot of notation here. It could be thick to read through, but it's actually very simple to understand. This upside down A, again, if you don't remember, means for every x inside of Rn, okay? My n space. Q is indefinite if I'm sometimes positive and sometimes negative, okay? So positive definite just means you're always positive. Negative definite means you're always negative, okay? That's really what's important. So some examples, we're not do actual examples, I'm just going to show you some graphs, okay? This is an example of positive definiteness in 3 space. Everything is always positive. The only time that I am possibly 0 is at the origin, right? The 0 vector. Negative definite is the exact opposite. I'm always negative, okay? So now let's just think about this quickly, right? If I have a function that could be modeled in 3 space, I am definitely interested in this point here because that is my maximum value. And I'm definitely interested in here because that is my minimum value, right? So for you physicists and engineers, that's something that you probably work with all the time, right? How do I have the strongest possible structure with the least amount of materials, with the least amount of weight, right? If I'm throwing a ball or something, what's the highest value is going to reach at, right? What's my maximum yield for the least amount of input, okay? So these are things that come up a lot in applications. Indefinite is something like a saddle, right? You have a saddle point, for instance. This is not the only case, but that's one. So I have negative values and positive values in my 3-dimensional space, okay? So that's really what we're talking about here, right? And again, remember, this function gives me a quadratic form. A parabola is a quadratic form. A hyperbola is a quadratic form. All those 3-dimensional conic sections, they are quadratic forms. So that's really what we're talking about here, okay? So let's cover a theorem and an example, and that'll be it for this video, okay? Let A be a symmetric matrix. That means it has to be n by n. And suppose it has a quadratic form given by x transpose A times x, okay? Then Q is positive definite exactly when A has only positive eigenvalues. So that's a nice way for us to relate our matrices to these conic sections that they put out in terms of just monitoring their eigenvalues, right? So the eigenvalues are all positive. Our quadratic form is going to be positive definite, right? So that's a nice way to be able to classify things by looking at their eigenvalue, okay? Same thing for negative definite. If our eigenvalues are all negative, we are a negative definite system, okay? If Q is indefinite, then we're going to have a mixture of positive and negative eigenvalues, right? So let's do an example. Let's determine the matrix for the quadratic form Q of x that is given to us by this function, okay? So before, what I did, or what we've done so far, is I've given you a matrix and I said find the quadratic form. Now what we're doing is the opposite. I'm giving you the quadratic form. What is the matrix that goes with it? I'm going to kind of reverse engineer this, okay? So let's just think about what this x transpose AX is. And let's actually just kind of multiply this out for the general case. Now, obviously, you can see here we have up to x cubed terms. Okay, so that means that we're going to have a 3 by 3, okay? Because the largest value we have is x3, so there has to be at least 3. They're symmetric matrices, so it'll be a 3 by 3 matrix, okay? Now, I'm not multiplying this out by hand right now, but if I were to take x1, x2, x3 as my column vector times the general 3 by 3 matrix, and then multiply that by the vertical x1, x2, x3, this is the position that each of those things come into, okay? And now, if you notice, the multiplication matches the subscripts, okay? An entry in this position would be A11, first row, first column. An entry here would be A12, first row, second column. A13. So notice x1, x3, x1, x2. It follows their subscripts, okay? So when I start to, so note that the indices match the subscripts. So when I start to try to build these things, okay, I'm going to relate the values I have in my formula to where they should go, okay? When I multiply two things to get x1 times x1, that's x1 squared. There's only one x1 squared term, and that's here. So that means this has to be -2. There's only one x2 squared terms. That means this has to be 7. There is no x cubed term, x3 squared, I'm sorry. So this is going to be 0. So I know my diagonal right away. -2, 7, 0. Okay, and that goes from here. Now these ones, okay, if you notice they're all even if they weren't, it doesn't matter, okay? Remember, this has to be symmetric. Okay, these matrices are always symmetric when they come about. So whatever I have here needs to match up with what I have here. So notice I have -8 x1 x2 for the x1 x2s. There's two ways for me to form an x1 x2 pair. That's with x1 x2 and also x2 x1. So the value for this coefficient gets split evenly here because this has to be symmetric. So that means that this -8 will split to a -4 and a -4. The x1, x3, that's here and that's here. So this -4 will split to a -2 and a -2. And this 2 here for x2, x3, there's two of those, x2, x3, and then the reverse, x3, x2, that has to split across here evenly. And that's going to give me all of my values. Okay, so I'm going to move on to the next screen. I'm going to re-summarize that in words, and then we'll show our thing, right? So A11, the indices for that first term give me the x1 squared term. So that has to be -2. A12 and A21 refer to x12 and x21 terms. And they're going to split evenly since my matrix is symmetric. Okay, so now you can see where that's written at, right? Same thing here, and so forth and so forth. Okay, so this, according to my quadratic form, okay, will give me this as an answer, right? And you can verify that on your own now. You can multiply this by x1, x2, x3 times this times x1, x2, x3, and you should get out our quadratic form that we have. Okay, so that's how you go backwards from your quadratic form into your symmetric matrix. Again, notice that it's symmetric, right? It's a symmetric matrix.